Hello, everybody. Welcome back. So now we're not going to talk Sudoku. We're actually going to talk computer coding, which is a kind of a different subject, but hopefully it'll be interesting to people who are interested in how computer solvers really work and what you need to do to create one of your own. Some of you may know Ranks, for example, has created a solver and published it, and you can even connect to it in one of your puzzle setting tools. Um, Before I start with this, I'm a software developer, by profession. So it's likely that at some point I'll mention something like bits or bytes or some stuff that's really technical and that you may not understand. So feel free to ask whatever question comes up in chat, and I will keep an eye on it and try to answer it. I will also try to introduce to you what it's like to code one, how it's really done, and how you can even, make your own software or even get started. It's not going to be very long, but I'm going to talk a little bit about that at least. And then I will dive into why coding your own solver is a bad idea. As you can see in the subtitle, I would really like to discourage you from trying yourself unless, and then we'll dive into why I wanted to try myself, and I will show you some coding examples and some things that you may want to know, and we're going to dive a little deeper. So hopefully the whole thing is going to last half an hour. But if you have questions or whatever, it may take a little longer. We'll see how it goes. And hopefully, Neverio can, for example, uh, look at the donations still coming in and interrupt me whenever he feels like it. It's all fine.
Yeah.
So,
If there's a big donation coming up, I will definitely mention it in the
yeah,
middle
yeah, please,
when there's
because
an empty space.
it's going to be hard to keep track of everything, and I want to give people and sponsors and donators all the attention that they deserve. But while I'm presenting, it's probably a better idea if I just focus on it. So let's get going. So let's first talk about what coding really is. Um, so one way to look at it is that you are kind of very free to create your own little machines where you put something in and where something comes out. If you make a plus machine and you put a 2 in and you put a 3 in, it spits out 5. Now, the only thing that makes coding really hard is that you'll have to tell the computer everything, every little single bit. So if, for example, you would want to code your own Sudoku solver, you'll have to tell the computer what a cell really is, what it means to be in a row together or a column together or a box together, and being aware of all the little relationships that come so naturally to humans. So that's what makes it harder, but also very interesting. And then there's the other thing that makes coding hard, and that's if you create your own little machine, you grab a tool, for example, or Legos or whatever. I mean, I think that's a better analogy. You just grab your building blocks, put them together, and it's a very physical activity. Whereas if you code something, you still have to type something in your computer, and it's not really something that you can touch. So there's a lot of things going on at the background, behind the scene, and inside the computer that you can see, but you still need to be aware of that it exists. You don't see all the bits and bytes and all the little electricity running through your machine, but to code really well, it's important that you know how things work. So if you look at the text there, it says talking to the computer. So you have a processing unit which takes care of running a program, and you tell it to do by giving it numbers. And then one number says you need to add the next two numbers that I give to you, which is just something that is hard for humans to understand. So instead, what we do when we code something up, we grab text files like you would make a Word, but instead of just writing in English, you use a computer language. And that's a weird kind of language, and it's very precise, and you have to use symbols and everything. But it's also a language that the computer will understand. And there's another program in the background, which is called the compiler, which is going to translate the stuff for you. And so if you code something up, you run the compiler, and then it runs, and then a program is running on your machine. It's kind of weird how just editing a text file is going to result in running software, but it really does work like that. So let me now move into why this is a bad idea to code up a Sudoku solver. Normally, if you code something up and you try something out or change the color on your web page or whatever, that's kind of easy. But coding a solver is actually one of the hardest things that you can do. Because you will need a lot of knowledge about how things work. Plus, and this is important, our human intuition for how large the solution space is of Sudokus is really off. It's a lot of numbers. I forgot how many solutions Sudoku really has without any givens. It's probably some at least billions, but probably even more. I can't even. I don't have any intuition at all for how big that really is. So if you look at the image there to the left, this is this famous legend that some chess players may know, that there was an advisor and a king, and the advisor invented the chess game, and then the king, I think, asked the advisor what the price for the game was, and then the advisor said, well, I want grains of grain, and I want 1 piece of grain on the first square, 2 pieces of grain on the second, and then 4 on the third, and 8 on the fourth. And then until you reach the 64 squares, and then until you reach the 64 squares, and then until you reach the 64 squares, and then until you reach the 64. It works the other way. Thanks for all the numbers. It's very good to see them because,
Speaking of numbers,
number is. It's incredible.
Speaking of numbers, we had 2 donations come in during that time. So Skojo, first of all, thank you so much for $25, and the Hat Girl also donated $25. So both of you, thank you really, really much.
Wow.
During that time.
That's funny. Okay, are we back? Yeah. Okay, I'm just continue talking. Um, so what I'm all and it, it felt always it felt a little weird, like that there's some kind of a ceiling to it. I'm not talking about shout outs. Yeah. But if you do a shouting contest, at some point you'll hit a ceiling, and then you try to be louder, and you put in so much energy, and still you can't seem to get any louder than you already are. And then how where does all the energy go? Um, so it's still there, and the energy is actually going into the air, but your hearing sort of makes it a ceiling. It's kind of hard to explain, but do you know about decibels? Like 1 decibel, I think it was like if you increase it by one, it's double the energy in the sound, something like that. The strength
Yeah,
of
it's
the
logarithmic, so
yeah, it's logarithmic. Yeah, so it's kind of the same with developing a Sudoku solver. That if you put in a lot of effort and you want to make it fast, for example, um, it's you'll have to live with little gain if you want to make it really fast. Um, Plus, yeah, it's an active topic of research. A lot of people, thousands of people, researchers have thought of all kinds of ways to make things faster that are on this scale. If you think that if you make a Sudoku solver because you want to make it faster than what's already out there, then you'll be very frustrated. Great. Um, so if you know all this and you understand how these things work, then you're in for a good ride, actually. Um, so the silver lining is that you can pretty much choose whatever language you like, what you're comfortable with, if you're already a programmer. Because if you use a slow language, for example, the only thing that will the only consequence that will have is that you can uh, bifurcate maybe three fewer cells or something, and on the scale of 81 cells, that's not going to be very much. So just pick whatever you like, and then go with it. I've also coded a solver in Haskell, for example, and it's got a reputation of being a very high level language and therefore slow. It doesn't need to be slow. I mean, you can definitely write fast Haskell, but if you want to write something quickly and you interpret it even, and you don't even compile it, then um, yeah, you can still use it as a solver. Um, so So let's go into what good motivations are. Um, so you can, for example, do it as a research project. Maybe you're curious. Um, was definitely true for me. I was very curious about how to do such a thing. Uh, like, what if I were to code a Sudoku solver? How am I going to do that? So it's kind of a practice thing. It's a challenge thing. Uh, it's even fun for me. So that's why I tried. And the result is that I've made a custom solver for myself, which which I have full control of, that I can adjust to my own needs. Like if I use a strange constraint and want to figure out how to put it in the solver, I can just experiment with it. So it's a nerdy thing, really. So if you're into all of that, then go right ahead. It'll be fun. So that's the point, and hopefully that will prepare you a little for the challenge if you want to do so yourself. Just one little thing. The code that I'm going to show you isn't going to be public. I don't want to publish it. I'm willing to show it to you. But if I published it, it would mean that I would have to give up the control that I have over the over my own project. Like there are many mistakes in there, things that are done weirdly, and that are really not very maintainable for the future. And I want to be able to work on whatever I like, and that's not entirely possible if I would publish it for people to use. So, but I will definitely be willing to help you with whatever you like and be a resource. So if you have any questions and you know how to reach me, you want to try doing one of these things yourself, I'm definitely game. I'm open to all sorts of questions. So go right ahead. So what exactly do you need to know? And I don't have a slide for this. I'm just going to go to code and web pages and show you things. So one thing that you'll want if you code a solver is to put in the right machines. Remember the first sheet. It says something about little and big machines. Now, if you're a good coder, you can sort of make fewer machines, if you know what I mean. If you make a couple of little machines and a couple of big machines, and you do it in a smart way, you reduce your own effort. I see a question from Riff Clown. I think that was the Sudoku Maker project, right? Is that correct? I'm not sure. Yes, it is. And I haven't. And that's well, I've used it, but I haven't looked at what's inside because it just works well, if you know what I mean. Plus, I kind of didn't need to because I've got my own thing, so that's why I didn't look into it. But it's definitely worth checking out, of course. What do you need? You will need to make. You will need to be smart about what machines you're going to make, the abstractions you're going to put in. So one thing that I did, and I'm not sure if that's something that I can show you right now, but is to make a distinction between visual elements and the logic that's behind it. So let me put up an example puzzle. Let me this F puzzles, by the way. So what I've done, for example, you could put a maximum in like this. Also, put a thermometer in like this. And now, I mean, this is just a demo, of course. But you could see that these are clearly two very different visual elements, but still they use the same logic in the background, which is that one cell has to be larger than the other. And so what I did in my code was to create a kind of a little machine for smaller than, with that particular kind of relationship. And if I see a maximum clue in the puzzle like this, I will translate it into little smaller machines saying, hey, there's a relationship between these two cells over there and the same kind of relationship between these two cells. Oh, we got a donation.
By Shai. Yep. Thank you so much, Shai, for the $50.
Oh, amazing. Wow. I'm so humbled. I don't know what to say. Okay. Yeah, another example which is interesting is this one. Like we could put an X here, and but I could also put a 10 cage, and these two are basically the same thing. So if you do the smart and you distinguish little pieces of logic and put that in and are able to translate the elements of the puzzle into the actual logic, but then you're actually very good to go, and you can do very cool things. So let me give you an example of this. I will have to run this thing. Uh, Now it runs off screen, but I can connect to this. It's pretty much like how it goes with the ranks solver. I use the same endpoint pretty much. Yeah, and ranks suite of scripts is definitely indispensable. You should definitely check them out if you're working with F puzzles. And shout out to Afraid Not To for maintaining this. It's amazing the work that they do. Yeah, I'm just so impressed. Anyway, back to my example. That's well, my mouse is doing things that I didn't want it to do. I've got a new mouse because I thought, well, I'm going to be streaming, so I need a new mouse, that kind of thing. I need to be prepared. But this mouse is very sensitive. Uh, so let me put anti-night in. I think that's a good example. And so cages, 17 cages. I am also going to put a 9 and a 10 clue in, I think this, and a given digit. So what this will do, I will tell you what the deduction is. So you have an 8-9 here, two 8-9 pairs. And this means that 8 and 9 cannot go in any of these cells over here in the green cells. But there's a small set of cells. I'm going to remove the green mark over there. You can see that there's a little group of cells over there. And there are 7 cells in this little group, and all cells in the group, they see each other. So it's kind of an extra region within the Sudoku, except that it's got only 7 digits because 8 and 9 are removed as an option from all of them. But this means that you have 7 cells plus only 7 digits. So it's kind of an extra region. And now, if you look at the one over here, you can see it removes the one as an option from there by anti-night and just regular Sudoku. The one cannot be here because 8 cannot go in the 9 cage, and the one cannot be here because 9 cannot go in the 10 cage. And now in this little region, 1 becomes a hidden single. Now, if anyone wants to turn this into a puzzle, that's fine, of course. Maybe I might, I don't know. But let me put the whole thing back in, or remove the digits and see what the solver does. And here you see that it places a 1 over there. And think, well, I think this is too small to read, but I think there is somewhere, yeah, it's this one. It says hidden single in group of 7 cells, and I think it's this little group over there. So that's things you can do with creating the right abstractions. So how do you really do this? Um, so I did some research, and this is kind of why I liked to do this thing myself. Was that can you read this? I think it says bronkerbos, and that's actually, if you look it up on Wikipedia, there's an algorithm that will find maximal cliques in a group of things. So it's very abstract, but what it means for Sudoku is that it will try and find largest groups of cells that all see each other. So that's, for example, a group of 9 cells or an extra region or whatever, but also a region like this, like we pointed out earlier. It will find this as a maximal region because it's maximal because there's not another cell that you can find that sees all of these 7 cells. So that's why it's maximal, and it's a clique because they all see each other. So what this algorithm does is it finds these maximal cliques and then recognizes them, and then the solver logic can use them and then put the 1 in and say, hey, I can do hidden singles in there. So that's one of the things you can do. Now, if you use like ranks solver, I don't think it will find this, but it doesn't really need to, because the ranks solver is much better at speed. It's much faster than my solver will ever be. So if you want, for example, true candidates, or if you turn on contradictions, for example, it will definitely find this, and that's perfectly reasonable. So why would you want to code this in the first place? It's not very useful, is it? But I did this because I was interested, and I was curious about it, and if how to implement such a thing. So yeah, but it's still I think this is worth a puzzle. So if anyone wants to create a break-in out of this, or a follow-up to this, then be my guest. I'm curious to see it. So another thing that's might be interesting. Let me revert the whole thing. So I've got the code in the background. I'm not sure if I should show it because it's very much code. But if anyone wants to see the code, then just let me know and I will guide you through it. But there's something else that I want to show you that you could also do in your solver, for example. Ooh, look. Okay, but let me first show you the pointing logic. Like you know how, for example, if 1 is restricted to these 2 cells, it cannot go anywhere over here, right? You can also generalize that and say, okay, let's put clue in an 8 gauge, which has a 1 in it. That's easy enough. And I'll put 26 clue in. Oh, let me turn off anti-night. Now, I'm choosing 26 because if you add up 2 to 7, you get 27. So this is the first number, or the maximum number for a 6-cell cage that needs a 1 in it. So it's kind of an edge case. And if this 8 cage needs a 1, and this 26 cage needs a 1, this 26 cage, well, the 1 in the cage is going to be somewhere over here. Now, if I put a 5 cage here, and I turn the solver on, this should turn into a 2-3 pair. And it does. So how is this done? And I can show you in code. So what a lot of solvers do is they go over boxes and over regions that they know. And they will say, okay, I've got a box, and if 1 goes in one of these 2 places, it cannot go in the 5. But this is a little different because now the 1 is spread out over 2 boxes, and I know people who won't even pencil mark it as such because this is kind of confusing. But still, the 1 does go in one of these 3 cells, and throws it out of the 5 cage. So how do you do that? So what I did was I define a set of cells that a clue really covers. So I call them figure cells. And let me go to, I think, final go. That's the think. Let me do the somewhat, I think. That good. Or yeah, I think this is a good one. Or maybe even this. Yeah. Okay. So this dives right into the code. So what this does, it's a global logic step, which means that it gets executed only once around, pretty much. Like it goes through all the clues and thinks about if there's any deductions it can make, and then if there's any change after it went through all the clues, it does globals, and this is one of them. What this does is it goes through all the logic of the puzzle, and then what it does, it asks every little piece of logic if it if 1 is restricted to a couple of cells. So I call this cells that must contain digit. So it asks, for example, this cage about, hey, look, 8 cage, I don't know what you are, but I know you're a clue, and I'm wondering if 1 is restricted to some cells in your in the grid, and so then the 8 cage says, yeah, I've got 1. It's these 3 cells that need to contain a 1. So if this is true, and that's what it does. It doesn't return any cells. And if it does, then yeah, there are some restricted cells, and then it will go through all clues that it affects, which is okay. And in this case, there's a row over here, which I will mark. And this row says, okay, has a couple of cells defined as well, and they overlap completely. And then the row says, okay, all cells overlap. I can do something with this, with the 1 being restricted in those cells, and which is that the 1 is removed from these cells. And that's what happens over here. Here it checks if there's a complete overlap. And this is true. If you can read it, it says, okay, you triggered logic, which is the row logic. One is indeed restricted to a couple of cells, and now you can do your thing and remove the one from your set of cells, or do other things. Like a killer cage could say, okay, I remove one from here, and I can change my sum, for example. So by doing it this way, this code is completely independent of the logic it's talking to. So the logic that's actually restricting the digit, and the logic it has an effect on, or the clue. So, and that means that it can do an extra step and say, okay, 26 gauge, you have a set of digits with one restricted in it. And then the 26 gauge says, yeah, I do. It's these three cells, the green ones, and then it will go over those. And then column 4 says, okay, I've got a complete overlap, and I can remove one from all the cells of these. So that's how that's done. So it's really worth it to make fractions that generalize, and so you can make really powerful deductions that way. Again, it's really how far you want to go with this. I mean, maybe your goals are different than mine. Mine were, hey, I want to make logic that generalizes the pointing logic, because I think that's very interesting. And if I do this, maybe it will come up with something new. And let's see what it does. And because I'm just interested in how these things work. But if you want to make things fast, for example, then maybe you shouldn't do this, because you're doing a lot of interactions and checking a lot of things, which are really maybe not even that necessary. So it completely depends on your goals, but it's still a good thing to just choose the right abstractions. That's something you'll have to do anyway. All right, so this is things you can do. And those of you who have looked at the window or screen already have probably seen this already. And this is not really a puzzle. This is about an abstraction that is very useful in the language that I'm using. And coincidentally, it's an abstraction that the ranks solver uses as well. And I should probably put this up. Look, I've got a chessboard ready for you. Now, what's a chessboard got to do with this? Well, very much actually, because it will allow me to explain what a bit field is. Now,
What's up, Kevin? Thanks so much for the $20.
Oh,
really appreciate that.
Fantastic. Wow. Yeah. Again, I'm humbled. Right. So maybe I really don't want to explain what binary counting is, but it sort of works like this. You have a 1, it still means 1, but if you do 1, 0, then it actually means 2 and not 1. So if you look this up, and I mean, of course, Wikipedia has a page on this. Yes, we are playing chess. Isn't that great?
The good thing is I'm not the opponent, because otherwise Qodec would wreck me, probably.
Yeah. But this square over here has 64 bits, which are 0, 1 values. So it's kind of a true truth value. It's always true or false. You can have two states, and that's a bit. So if you put 64 of them together, you can make numbers out of them. Yeah, that's exactly the joke that's appropriate here. But what you will see is that if you research how chess engines are made, which is not the same kind of software, but it's also very hard because there's even a computer engine world championship out there, which is running continuously, where the best computer engines in the world are competing against each other, and they are so incredibly strong that it's jaw dropping. I mean, they play moves that I don't really understand anymore. But one of the things that you have to do is to pick some kind of representation of the chessboard. And if you for example, do a simple solution and say, okay, I've got 64 squares, and for each square, I just want to know what's on there, like a rook, a white or a black rook, or a black or a white pawn, or whatever. And there are, I believe, 13 different options for it. Then you can choose that representation, of course. And I wrote a chess program as a teenager, and that's how I did it. But it's not going to make your chess engine very fast if you do this. But why is this? Why is a chess engine not very fast if you choose a representation like this? And that's because if you want to figure out moves or want to evaluate the position, what you're going to have to do is ask a lot of questions to the chess engine about where pieces are. So it's always going to be about questions that cover the entire board. So if you choose a different representation format, then you can maybe use the CPU's capabilities to make it faster. What they've done is created bit fields. And what this does, and it's no coincidence that, this is 8 rows and 8 columns, like the chessboard over here. There's also 8 rows and 8 columns. So I'll show you how it's done. So one thing that you can do, for example, is encode where pawns are. And that's a true-false thing. It's a bit. You can just record for each square on the grid where a pawn is and something else. It might be empty. It might be a different piece, but you're really only interested in where pawns are. And so what you do, maybe I should turn off the conflict highlighting. So now, off. Okay. Otherwise, everything is going to be red. So let me put zeros in, and then put ones in these 2 rows. You should color them, but you can see that everywhere where a 1 is, there's actually a pawn here on this diagram over here. It's the same thing. So this is 1 bit or for each square, and then if you put 64 of them together, you get a number which a computer can understand, and that it can use to make calculations with very fast. But that's good. So what if you, for example, want to know where white pieces are in the starting position? Then you would this number, and put 64 bits together and create another number. And this is where all the white pieces are in the starting positions. They match precisely. Now, there's an operation the CPU can do, and it's called an AND operation. And what that does, it compares every 0 and every 1 in every position of two different numbers. And if they are both 1, then it will make it a 1. And if one of them is a 0 or both of them, it will make that a 0. If you do this operation, which is a very fast one, and you put them together, and let me do so by using colors now. I think that's more reasonable now. I'll make yellow, or no, blue. I think blue is good. Blue for where pawns are, and I will do red for where white pieces are, both in the starting position. Now, if you want to know where white pawns are in the starting position, see, if you use this operation, it will only select these 8 bits. And this is a very fast operation. So if you choose a good set of numbers to represent the position, your chess engine is going to be very fast. Now, if you want to make your Sudoku solver fast, so let's come back to Sudokus, you can do the same thing, except it's not going to be a single one per square in the grid. But what you can do is put options in and say, okay, all things, all cells have 9 different options. And what you can do is say, okay, I'll use 9 truth values for this, and say, okay, if it's all of them are 1, then I can put all digits in. And if they're all 0, then I've got no options left and the puzzle is broken. So that's actually a very quick way to figure out when a puzzle is broken. If one of the cells is a 0, then you've got a broken puzzle. And if one of them has exactly 1 bit left, and there is an operation a CPU can do, which is to count the number of 1 bits in the number. And if 1 comes out, then you know that it's actually a naked single. So that's a very fast way of detecting a naked single. So how does this look? I don't think it will show very much in the code. I mean, it's just going to be numbers. So it's going to be very obscure. The place where you can see it is here. You have a list of values. Let me go here. Look, and if you've never seen syntax, then this is hard to read. But what this means, the public means something about access. Who can actually read this? So that's not really important right now. The ulong, what that is, it's a number with 64 bits and without a sign, so it's not having a minus or a plus sign. And that's called ulong. It's an abbreviation for unsigned. That's the U, and the long means 64 bits. And this bracket thingy over there means that you create a list out of them. And in this case, it's going to be 81 values. So you got 81 of these bit fields, ulongs, that you could perform really fast operations on. Now, if you are going to use ranks solver, for example, or even working on it, then you will see that the ranks solver uses it too, and you know how fast it is. So it's a result of choosing the right kind of abstraction.
Also, Jacob had a question. He asked, when you are creating solvers, are you treating all the digits for a cell as only a char, like a character, or a whole value?
Yeah, that's a really good question, because if you use these bit fields and imagine that, let's say, well, this has 8 fields, but if if I put 8 ones in, it means that I can put an 8 in, or a 9 or a 7 or 6, each number. But if I put this, then actually the cell is a 1. So the value of a cell is actually encoded into this number. It's just that 1 maps to a 1, a 2 maps to a 2, but then it breaks. A 3 actually maps to a 4, which is 2 times 2, and a 4 maps to 8, which is 2 times 4. Now, if you have 15, which is 1 plus 2 plus 4 plus 8, that means you can put 1, 2, 3, and 4 into that cell. So it's kind of a mix. It's sort of blended into one giant number, a combination of the numbers. Anyway, this was what I want to tell about coding your own solver. It's I think there's a lot more to tell, but if you want to do this kind of thing yourself, I just recommend just to get going and see where you end up. It could be good. And if you have any questions after this particular section, then and you know where to find me, then you're welcome to. Hopefully, this was fun. I think it's a good time now to go to a break, and then we do. What do we do? Do we do?
We actually roast our own puzzles.
What?
Apparently, the incentive for that has been met. So yeah, we have prepared a few of our own puzzles where we are going to be roasting in terms of like what we didn't like about those puzzles when we set them.
Yeah.
So we are going to talk about those for a while.
Okay, that's going to be fun. I'm looking forward to it, actually, because I have some grudges against my own puzzles, so it's great to have a chance to get them all out. Great. Okay, so let's go on a break then, and we'll see you back in a couple of minutes.
Well, okay, we might have some technical difficulties changing the screen, but yeah, the DT thought is going to come soon, hopefully. Well, if they don't, we are still trying to entertain you guys as much as we can. Now we can like hum the melody if people want to.